This is the outline of my presentation. So today I would like to talk about analog versus digital circuits. What is the difference between analog and digital? Okay, so what is the difference? And I'll talk about the digitization of analog signals. And if I have time, I would like to introduce binary numbers. Okay, next lecture, I'll talk about number systems, number system conversions. So all of these topics will be covered during this week, inshallah. Okay, so let me start first with analog versus digital. Can anyone explain to me what is the difference between analog and digital? Any idea? Anyone?
Analog is infinite.
Okay, and
Well,
digital
is limited. It's countable.
Can you be actually more specific what you mean by actually infinite?
It's like analog is real numbers. It can be anything in the range of real numbers. While digital is only integers. You can count it.
Okay, now you are actually more specific. Yeah, good description. Okay. Type. So the way that anyone else would like to have like a definition for analog versus digital?
Analog variable physical and digital. It is digital. You can.
I can't hear you. Can you raise your voice again? So analog means what?
Variable physical, and digital means in computer. We can catch it.
Okay. Okay. So basically, you are saying that analog is something which is physical, whereas digital means that something that you are storing inside a computer, right?
Yes. Yes. Virtual. Yeah.
Okay. Okay. Good. 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 Yeah, you have really a good idea about the difference between these two. Okay. Two important concepts. So, so analog here. Let me just move my mouse. Okay, back here. So analog means continuous. Okay, like someone said, real numbers. Okay, so when we talk about an analog parameter, okay, it can have a continuous range of values. It does not really have to go to infinity, but continuous. Okay, it means continuous. Okay, so for example, temperature is considered to be an analog parameter. So the temperature, it increases and decreases continuously. Okay, so that's actually, you can think about analog, you can think about temperature as an analog parameter. It's like a continuous mathematical function. Yani, for example, if the temperature outside now is 40 degrees and it wants to go up to 41 degrees, it's going to go continuously. It does not really jump from 40 to 41 suddenly. It goes from 40 to 41 continuously, right? So you have actually a continuous range of values between 40 degrees centigrades and 41 degrees centigrade. Okay, so that's temperature, which is an example about an analog parameter. You need, of course, a temperature sensor, okay, to sense the temperature. Do you have other examples about something which is analog? Any other example?
Maybe velocity or speed.
Yes. So if you are measuring, let us say, the speed of a car or the speed of anything, of any object, yes, so that will be, for example, something which is called an analog parameter. Yes, excellent.
Time it takes something to do something.
Something about, can you be
Time.
specific?
Time. Measuring time for something.
You mean time? Time,
Yes.
time. Time itself, yes, is continuous. Yes, time itself is continuous. And you can think about time as an analog parameter. Okay, good. On the other hand, we have digital. It means digits. It comes actually from digits, so numerical digits. So you have a fixed set of discrete values. For example, the number of a month, okay, it can be from 1 to 12. You can have a month number to be either 1, 2, 3, and so on, up to 12, but you cannot really have the month number to be, let us say, 1.5. 1.5 is not a month number, right? It is either 1 or 2, but not 1.5. So you can think about the month number as a discrete value, as it can be represented by a digit. So we call it actually a digital parameter. We call it a digital parameter. Do you have other examples? Other examples about a digital parameter, other than the month number? I just gave one example here. Give me another example about something which is like a digital parameter. I cannot hear anyone.
The charge of the battery of a phone or a tablet or any device.
The charge. Okay, but really it's representing it in digits, but really the charge is increasing continuously, right? So when you are charging a battery, the charge is increasing continuously over time, but it's showing it as digits. Okay, but so we cannot consider this really as a digital parameter.
I have an example. The number of absent I have in this course.
Okay. Okay, good. Okay, so that actually can be considered to be something which is a digital parameter. Or you can say the number of days, okay, the number of days in a week, or the number of days in a year, okay, that actually can be counted as a digital parameter. Okay, good. So now we understand the difference between analog and digital, okay? So analog means continuous, digital means that you can represent it with numerical digits. Good. Now, do you think computers are analog or digital systems? Are computers analog or digital systems? What do you say?
Digital.
Yes, of course, digital. Everything is represented inside a computer system. It's represented with digits. Yes, it is actually a digital system. So computers are digital systems. So do you think that which is easier to design, an analog system or a digital system? Which one is easier?
Digital.
Digital, yes, of course. Digital systems are a lot easier to design, okay, because they deal with a limited set of values rather than an infinitely large range of continuous values. So for this reason, digital systems are easier to design. Now, the world around us is analog. Okay, so I talked about temperature. You can talk about speed, acceleration. All of these are analog parameters. So it's common to convert these analog parameters into digital form. Sound, for example, is an analog form. Okay, it's an analog so sound itself is analog. But what you can do is that you can digitize, okay, the sound, and you can store it as digits inside a computer system. So this process of converting an analog signal into a digital signal is called digitization. Okay. So this is an example of digitization of analog signals. So you want to convert an analog signal into a digital form. So the analog signal is a continuous signal. Okay, it's like a continuous function in mathematics. Okay, so here's an example of an analog signal, and we are representing it as a function. And you can see that we are representing time and the voltage. So time here is the x-axis and the voltage is the y-axis. And you can see that how the signal is going up and down over time. Now, if you want to digitize, okay, the analog signal, you need to represent it with specific voltage values. So you can choose specific voltage values like V1, V2, V3, and V4. These are only 4 voltage values. And now you have to decide, okay, what's the value of the signal at a given point in time? This is shown in the next slide. So you can see the analog signal, and at each point in time, we have to decide whether the value is V1, V2, V3, and V4. Now, this is an electric signal, okay? So here it's represented with a voltage electrically, okay? We don't really care about these values, V1, V2, V3, V4. All what we are caring about is that, okay, there are only 4 possible values. So when we digitize an analog signal, we assign, okay, a value, okay, to the signal. So after actually digitizing it, it becomes as shown below. Okay, so now we have converted the analog signal into a digital signal. So it can be V1, V2, V3, and V4, but nothing in between. Nothing in between. Only these 4 possible voltage values. Now, which one do you think is more accurate? Is the analog signal is more accurate or the digital one?
The analog.
The analog, yes, because it can represent all values between V1 and V2, and all values between V2 and V3, and between V3 and V4. All of these values can be represented. And if the voltage goes above V4, it can be represented with the analog signal, but it cannot be represented with the digital signal. So the digital signal can only represent only 4 possible values. So now there is a loss of accuracy. Okay, so once we have converted the analog signal into digital form, we have lost accuracy, right? So how to improve the accuracy of the digital signal?
We can increase the range of voltages.
Yes, so we can actually add more voltage values. So between V1 and V2, we can introduce more. Between V2 and V3, we can introduce more. So therefore, we can actually add more voltage values. So rather than having only 4, we can have 8, we can have 16. We can even have more, right? So the more voltage values we have, the more accurate, okay, the digital signal will become. That's really the idea, okay, to improve the accuracy of the digital signal. Is this clear? Do you have any question about this?
Doctor, when you say add more values, do you mean add more values between the already existing 4 values?
So right now we only have V1, V2, V3, V4, right? Now between V1 and V2, I can actually add another voltage level. I can actually add another voltage value. So I can actually have, okay, between V1 and V2, I can actually have, let us say, a voltage value in between, and this will make it actually more accurate if you have the voltage around this value. The same thing between V2 and V3, the same thing between V3 and V4. So rather than representing, okay, the voltage with only 4 possible values, so you think about V1 to V4 as 4 possible digits, okay, 4 possible digits. And we are storing this digital signal using only 4 possible values from 1 to 4. If you double them, if you make them from 1 to 8, okay, then basically these voltage values will be closer to each other, and the digital signal will become more accurate and very close to the analog signal. The more voltage values that you add, okay, so these voltage values will be stored inside the computer system as digits, and therefore the more accurate the digital signal, it will become more accurate.
Yeah, but
Okay?
you will still distribute them over correct numbers, right?
So exactly. So now you can actually have something between V1 and V2. So V2 actually can be closer to V1, and V3 can be closer, and so on. And so we can actually have V5, V6, V7, V8. Okay. So basically, we can actually have these voltage levels closer to each other, and therefore we can actually have a more correct, okay, or more
precise number,
more accurate representation, yes, of the digital signal. Oh, so now the world around us is analog. So for example, look at sound. Do you think that sound is analog or digital? Is sound analog or digital?
Analog.
Analog, yes. So basically sound is like vibrations, right? So when you have the sound waves, the sound wave is going to vibrate, okay, the air, okay, the air molecules, okay, and then it's going to reach your ear and enter your ear. And then once it enters your ear, the brain is going to interpret this sound. So I'm talking now to you, right? So basically the sound is coming out from your speaker into your ear, and the brain is trying to interpret, okay, the meaning of this sound, okay? It's converting the sound pattern into some kind of a meaning. So the sound itself is analog. So now I'm talking actually to you, right? So my input here is the sound, which is an analog signal. Now the sound is going into my microphone. Okay, so the microphone is acting as an analog to digital converter. So this analog to digital converter is very important because it will convert the analog signal into a digital form. Okay, so you can see here on top, okay, I have here the analog to digital converter. So think about sound here, okay, as my input. So the microphone here is acting as an analog to digital converter. So it's taking the sound and converting it into a digital signal and storing this sound. You can actually store this sound, okay, as digits. So you can actually have a sound file and you can actually store them as digits inside your computer system. Okay. Now, in my case, okay, the sound will be what will happen to actually to the digital signal. So once the analog digital converter has converted this sound, so now this sound is a digital signal. So basically, it can be stored as a sound file inside the digital system on a computer system, for example, or it can be transmitted through a network as a digital signal. Now, over the network, okay, your computer system is receiving my sound as a digital signal. You can actually store it. It can be processed. Your computer system is a digital system. Okay, so you can actually store it. You can actually do anything to the sound file that you are storing. Okay, you can process the sound if you want to. But then you can actually here receive it, okay, on your computer system as a digital signal. And once it is received on your computer as a digital signal, your speaker is acting as a digital to analog converter. So it's converting the sound from its digital form back to the analog, so that the speaker is actually again transmitting the sound, okay, to your ear so that you can understand what I'm saying. Okay, is this clear? So you can see that the world around us is analog. I just mentioned the example of sound as an analog signal. So we need analog to digital converters, okay, to convert the analog input into digital signal. Now, this digital signal can be stored or it can be processed by a digital system, like a computer system. Okay, so the computer system is a digital system. And now when you would like actually to, let us say, to transmit the digital, let us say, sound over a network and receive it on another computer system. So once it has been received and you would like to hear the sound, there is another converter that will convert the digital signal, the digital sound, back to analog. So it will output, so the input to the digital to analog converter is a digital signal, and the output will be the analog signal. For example, the speaker that you have on your computer system is a digital to analog converter, okay? And once it outputs the analog signal, the sound wave is going to reach your ear and you will understand what I'm saying. Is this clear?
Yes.
Do you understand this?
Clear.
You understand this?
Yeah.
Okay.
Yes.
So the way that the sound is stored on your computer system, it's stored in a digital form. However, the sound itself is an analog signal. So therefore, it has to be converted from analog to digital in order to save it in a file, okay, as a digital sound on your computer system. And later, if you would like actually to play this sound file, or you would like to hear it, there is another converter that will convert the digital signal back to analog. So this is called digital to analog converter, which is shown at the bottom, okay, that will output, okay, the sound, okay, back into its analog form. So it becomes a sound wave, and therefore you can actually hear it, okay? Now, our focus in this course will be on the digital system, which is shown in the middle here, which is shown in yellow, okay? That's our focus in this course. So everything, so all the input to the digital system will be a digital signal in digital form, and all the output will also be a digital signal in digital form. So our focus in this course is called Digital Logic Design. That's the title of our course. So we are dealing only with digital input and digital output. We are not dealing with analog. Okay, so electrical engineers, they deal more, they have two types of circuits. They have digital circuits and they have analog circuits. In our case, our focus will be on digital circuits and digital systems. We are not dealing here with analog, okay, circuits or analog signals. Okay. So we understand the scope of this course. So everything that we are talking about in this course, we are talking about digital systems and digital logic design. Okay. Any questions about this?
Everything is clear.
I still actually have only a few minutes, 5 more minutes. Right. Let me talk about binary, okay, numbers. Now, how do computers represent digits? So as I said, a computer system is a digital system. So everything which is stored inside a computer system, it's stored as digits. I mentioned the example of sound. So the sound itself is converted from analog into digits and stored as digits inside the computer system. The same thing for images, the same thing for video. Everything is stored inside the computer system as digits. But how do computer systems represent digits? Any idea?
Zeros and one?
Exactly, in binary. So we only need 2 digits. Now, we human beings, we use 10 digits from 0 to 9. We are used to the decimal number system. Okay.
A combination of zeros and ones that represents the.
We can actually represent anything. We only need 2 digits, only 2 digits. So we call them actually binary digits. So binary means 2, okay? So binary digits, we only have 2 digits, okay, 0 and 1. These are the simplest to represent inside a computer system. So for example, you can use an electric voltage. You can use, for example, that in processors and digital circuits. Okay, so this will be our focus in this course. So high voltage here will be, let us say, around 1 volt. That will be the digit 1, and the low voltage, which is around 0 volt, this will be the digit 0. So here you can see that, okay, the voltage level, which is used inside the electronic circuits, inside the digital circuits. Okay, so we have low voltage, that will be digit 0, and high voltage, which is digit 1. What I mean here by high voltage, I don't really mean actually very high. It means like around like 1.2 volts. That's it. Even today, modern processors, they are actually using voltage even below 1 volt, sometimes 0.7, 0.8 volts. That's actually considered to be high voltage. In the past, people used like 30, 40 years ago, people used actually 5 volts. Okay, so high voltage was around 5 volts. We don't really care too much about the voltage value, okay, or the voltage level. All what we care is that we are using actually here high voltage for 1 and low voltage for 0, okay? That's actually using electric voltage. We can use electric charge, okay, for example, inside the memory of a computer system. So inside a memory cell, inside the main memory of a computer, people use tiny capacitors. So when they charge the capacitor, they are storing a 1. And when they discharge the capacitor, they are storing a 0. So they use actually a very tiny electric charge to charge the capacitor and to discharge it. And this way, okay, you are storing. So if the capacitor is charged, we call it logic 1. And if the capacitor is discharged, they call it 0. Okay, so we can store the 1 and the 0 as an electric charge. Okay, you can actually have billions of these capacitors inside today a memory chip. We can use magnetic field. That's another way, a third way, okay, of storing a 1 or a 0. This has been used actually for like 6 decades. Since the 1960s, people have invented magnetic disks and even magnetic tapes, okay? But magnetic disks actually are very popular. So people, for example, store files on a magnetic disk. You can actually have an external magnetic disk, or you can have it even inside your computer system. So people use actually the magnetic field to store 1s and 0s based on the polarity, okay, of the magnetic field. They can actually store 1s and 0s. So on a magnetic disk, you can actually store billions of these bits on the surface of the magnetic disk, okay? So we are using here the magnetic field to store the 1 and the 0. Very simple, okay? The idea is simple. All what we need is just to store 2 possible values. Or even using light. People use light in optical disks, and they use optical lenses. And also they use sometimes in optical networks, okay? High-speed networks. They use light, okay, to transmit 1s and 0s, okay? And usually there is an optical lens that can sense the light, okay, whether actually, so it senses whether you are actually transmitting or storing, let us say, a 1 or a 0. So there are different technologies today, okay, that can represent the binary digit, the 0 and the 1. Is this clear?
Yes.
Students, are you with me?
Yes.
Okay, very good. So now we have seen actually different technologies, okay, that are used today to store the binary digit. So the binary digit is called the bit, okay? So bit means binary digit. So they take here the B, I, and the T, okay? That's actually is the bit, okay? It means either a 0 or a 1. So let me pause here, it's time. Okay, next time I'll talk more about the binary number system. I'll talk about number systems in general. So my topic today will be about binary numbers. Everything stored inside the computer system is in binary. So whether we are storing numbers or we are storing fractions or negative numbers, signed, unsigned, okay, characters, symbols, images, sound, everything is stored in binary. It's a lot easier to represent numbers in binary rather than in decimal, because the way that the digital circuits represent numbers in binary using only 2 voltage levels, okay, high voltage and low level to represent the 1 and the 0, makes it a lot easier to deal with binary rather than with the decimal number system. So we human beings, we are used to the decimal number system, but computers prefer to use the binary number system. So for this reason, I need to talk about binary numbers and how to convert between binary and decimal in great details. Okay, so this is my topic today. Okay, so remember that binary means 2. And a binary digit, which is also called a bit. So bit means binary digit. It can be either 1 or a 0. Now, let me just go here back, okay, and show you, okay, how we can represent a number in binary. Now, a single bit can only represent two values, 0 and 1. You cannot really do much with a single bit, but you can take a group of bits, for example, 8 bits to represent a number. So here I'm showing 8 bits, and these bits are numbered, okay, from bit 0 to bit 7. So bit 0 here is the least significant bit, and bit 7 is the most significant bit. So we start at 0. Okay, so the least significant bit appears to the right, the most significant bit appears to the left. Since we start at 0, so the most significant bit will be 7 if we are using an 8-bit number. Now, each bit has a weight. Okay, so it has a position and it has a weight. So the weight of bit 0 is 2 to the power 0, which is just 1. And the weight of bit 1 will be 2 to the power 1, which is 2. Then we have 4, 2 to the power 2 is 4, 2 to the power 3 is 8, then 16, 32, 64, and 128. So this is an 8-bit number, and each bit has a weight. So the weight depends on the position of the number, of the bit inside the number. Now we can, yes, go ahead. Question?
The last sentence, 7-bit.
No, we are dealing with 8-bit number, but we are numbering the bits from 0 to 7.
Yes, before this slide.
Yes.
Bit 7 in an 8-bit number.
So bit 7, yeah, well, this is bit 7 here, which is shown as the most significant bit. Let me use my highlighter. Okay, so I'm going to use a highlighter here. Okay, you can see this is bit 7 here, right? That's actually bit 7 that has the value 1. This is an 8-bit number. So the most significant bit is bit 7. The least significant bit is bit 0. So the bits are numbered from 0 to 7. Now this number consists of 8 bits. We call it a byte. Okay, so a byte inside the computer system consists of 8 bits. So you can use it to store an 8-bit number.
Yes,
okay.
I get it. Thank you.
You get it now?
Yes, thank you.
Okay, so now we can say what's the decimal value of a binary number. So each bit has a weight, and this weight is a power of 2. Okay, so you can see it here, 2 to the power 0. This is for bit 0, 2 to the power 1 for bit 1, all the way here to the most significant bit. Okay, so the most significant bit is bit 7, and the weight is 2 to the power 7. Now, if I would like to calculate the decimal value of a binary number, what I have to do is that I have to take each bit. So I'm calling it digit 0. The 0 here is bit 0. I have to multiply it by 2 to the power 0. Then we go to digit 1. Okay, that will be bit 1. It will be multiplied by 2 to the power 1, which is simply equal to 2. Then digit 2 will be multiplied by 2 to the power 2. 2 squared is equal to 4. All the way to the most significant bit. Now, if we have n bits, the least significant bit will be bit 0. The most significant bit will be bit n minus 1. So this is digit, okay, or bit n minus 1. So I write it dn minus 1. This must be multiplied by 2 to the power n minus 1. Here's an example of a number which is shown in binary. Now, this 1 here is just a 1. This is a 0 multiplied by 2. Multiplied by 2 is just 0. This 1 here must be multiplied by 4. This one is multiplied by what? What's the weight of this one? This one here is multiplied by what?
3.
8. Then this one will be multiplied. This will be what? This one will be what?
16. 2 to the power 4.
Yes, 2 to the power 4 is 16. Then we skip the 0. We skip the 0. Now this one is what? What is 2 to the power 7?
128.
128. So I'm going to add 128 plus 16 plus 8 plus 4 plus 1. Now, if I do the math, if I add 2 to the power 7 is 128, 2 to the power 4 is 16, 2 to the power 3 is 8, This is 4 plus 1, you get 127. So this number here, which is shown in binary, it has the decimal value, which is 127.
Why did we skip the zeros?
This is the decimal value of a binary number. So if I would like to represent 157 in binary, I'm going to represent it as 1001 1101. Okay, that
Doctor?
will be the, yes, go ahead.
Why did you skip zeros?
Because 0 multiplied by anything is 0.
Oh, makes sense.
Okay, so 0 multiplied by 2 is 0. 0 multiplied by 32 equal to 0. 0 multiplied by 64 is equal to 0. Of course, you can actually add plus 0, plus 0, plus 0, but this does not change the value of the decimal number. Okay? So therefore, we only have 2 digits in binary, 1 and 0. If it is a 1, you look at the weight of the 1. If it is 0, you simply just add 0, so it does not really change the value of the decimal value of the number. Okay, is this clear? Right. So now it's actually important to remember some common powers of 2. If you would like to do it this quickly by hand, it's important to remember these powers of 2. So 2 to the power 0 is simply equal to 1. 2 to the power 1 is 2. Then we have 4, then 8, 16, 32, 64. 2 to the power 6 is equal to 64. 2 to the power 7 is equal to 128. So it's important to remember some of these common powers of 2. 2 to the power 8 is 256. 2 to the power 9 is 512. And 2 to the power 10 is equal to 1024. Now, this is interesting. Okay, when you look at 2 to the power 10, it's slightly more than 1000. It's 1024. So remember these powers of 10. You can go all the way here to 2 to the power 15, but I'm going to stop here. Okay. So it's common to remember these powers of 2 because we use them frequently when we are dealing with binary numbers and would like to obtain their decimal values. Would like to convert the binary number into decimal. Is this clear? Right. So the binary number system and the decimal number system are called positional number system. In the past, before people have invented the decimal number system, people have used, for example, the Romans have used the Roman numeral. So they used letters to represent numbers. For example, X here will be 10. So you have here 10, and you have another X, which is another 10. So this will be 20. And then the V will be 5. So this will be 25. And then the I will be 1 and another 1 here. So this will give you 27. So 10, 10, 20 plus 5, 25 plus 2 is equal to 27. Today, if you would like to write 27 in decimal, you write 2, 7. You know that this 2 here is positional, it's 20. And so this 2 must be multiplied by 10, so it becomes 20. Plus 7, it becomes 27. So this is the decimal number 27. So we use Radix 10. Now, the meaning of Radix 10, it means that we have 10 digits from 0 to 9. But you can write a number, okay, consisting of multiple digits, and each digit has a position inside the number. This is why we call it a positional number system. So the decimal number system is a positional number system because each digit in the number has a position and a weight. On the other hand, the Roman number system is not positional. Okay, you can write the X anywhere inside the number and the X is still 10. Whereas the digit here that you write in a positional number system has a weight. So this 2 is not a 2, it's a 20. Okay, and this 7 is just multiplied by 1. The binary number system, we call it Radix 2 because we only have 2 digits, 0 and 1, is also positional. So this is the binary number system, okay? So it's called binary because it's only 2 digits. So if you look here at this binary number, which is 11011, Okay, you can say, well, this is an example, 11011. This is just a 1, this is 2. Okay, this is 0 multiplied by 4 is just 0. This is 8, and this is 16. If you add them up, you get also 27. So 11011 is also 27. So this is how you present the 27. In binary, this is 27. In decimal, and this is 27 according to the Roman, okay, Roman, using the Roman numerals. Is this clear? Students, is this clear? So we can actually represent numbers in different number systems. Okay. Now, as I said, that computers prefer, okay, the binary number system, as we have seen last time, because it's easy to deal with only 2 digits only, 0 and 1. On the other hand, we are used as a human beings to the decimal number system. Do you know why we use the decimal number system? Any idea? Why did people invent the decimal number system? Why do you
because
think?
it's easier.
Yeah, why it's easier to deal with decimal?
Because
It's straightforward.
Because
You
you
don't
can-
have to recalculate it or something.
I mean, why people, why our ancestors have invented the decimal number system thousands
because
of
you
years
can
ago?
because you can represent big numbers with a few letters.
No, we are talking about the decimal number system. Okay, so why did they invent decimal? Why they did not invent binary?
To be more accurate.
Why do you think that we have decimal number system actually until today? People have invented this hundreds of years ago, right?
Because
Why do we have
want,
decimal? Why do we have 10 digits from 0 to 9?
because, for example, if we wanted to write a number like 3000, if we will write it with the binary numbers, it will take like forever.
What I'm asking is, okay, why do you think that people thought about the decimal number system? Okay, in history, if you just go back to our ancestors, why they did invent decimal? Why it's natural to us?
اتوقع انه عشان يعطيك خيارات اكثر من البرايمري.
They could have invented binary from the beginning, ones and zeros, that's it. Why did they invent decimal? Why?
Because you can use a scientific method, scientific notation, I mean.
No, the answer is simple, because we have 10 fingers. Okay. We have 10 fingers. If you look actually at, if you would like to teach a child to count, you teach him to use his fingers, okay? So people actually use their fingers to count, and because we have 10 fingers, they thought about the decimal number system. Okay, it's that simple. Because we have 10 fingers, this is why the decimal number system is natural to us, okay? If we only had 2 fingers, then we would have used actually binary. It's that simple, okay? So this is why the decimal number system is natural to us, because we have 10 fingers, okay? Let us take a look at this number. Now you can actually use any number system, okay? For example, the octal number system. The octal number system has only 8 digits from 0 to 7, okay? Only 8 digits. If we had only 8 fingers, we would have used the octal number system. So we can actually count from 0 to 7. Okay, we'll only have actually only 8 digits. So for example, this number 2107 in octal, you see that I'm writing 8 here? That actually is the radix. So 2107 in octal, what is the value? What's the decimal value of this number? Any idea? What is the decimal value of 2107 in octal? Well, just use this equation here.
Is it a mix between the 2 equations?
Use this equation. You know, this is the equation. What is the radix r? The radix r is 8. Okay. What is d0? It is 7. What is d1? It is 0. What is d2? Is 1. What is d3? It's 2. So we have here 4 digits. Digit 0, digit 1, digit 2, digit 3. Now this is in octal. So we are using the octal number system. So we have only the digits from 0 to 7. So if you look at this number here, 2107, this is 7 multiplied by 1. This is 0 multiplied by 8. This one is multiplied by what? This one here is multiplied by what?
8 to the power 2.
8 to the power 2. Yes, it's 64. And this 2 is multiplied by what?
8 to the power 3.
Yes, it's 8 to the power 3. So just do the math and you will get the number 1095. So the decimal value of 2108 in octal is 1025. So we can do a conversion between different number systems. Okay. So in octal, this is not 2107 because this is not decimal. This is not 2000. It's not 1000. It's 2 multiplied by 8 to the power 3 because the radix or the base here is 8. And the position of this digit is actually at position 3. So we multiplied by 8 to the power 3. This one is multiplied by 8 squared. This 7 is multiplied by just 1. So therefore, we get the number 1095. So this is in decimal. So when we say 1000, it means 1 multiplied by 10 to the power 3. When we say 95, this 9 is multiplied by 10 to the power 1. And this 5 is just a 5. Notice that there are 0 hundreds. This is the importance of the 0. If there are no hundreds, we write a 0 at this position. So it's 0 multiplied by 100. Okay? So it's 1095. There are no hundreds here. Okay? Is this clear? This is what I mean by the positional number system. You can choose whatever radix. So in decimal, the radix is 10. We have 10 digits. In binary, the radix is 2. But we can also use actually another radix. I can choose the radix to be 8, like in this example, or I can choose the radix to be, let us say, 5. Okay. So we can actually choose the radix to be actually 8, 5, 2, 10, whatever. Okay. So the math applies actually to any radix. That's why we call it a positional number system, because each digit has a position in the number. Let us move on. Now, to convert, okay, so to convert actually the number in any radix to decimal, we use this equation, which is shown here in yellow, okay? So D0 is just digit 0, D1 is multiplied by the radix R, D2 is multiplied by R squared all the way to the n minus 1. This will be the most significant digit. It's multiplied by R raised to the power n minus 1. Of course, depending on the value of n, okay? The number of digits inside the number. How about if I would like to convert a decimal number into binary? How do I do this? If I have a number in decimal, how do I convert it to binary? Any idea?
We can divide the number by 2 and take the modulus.
Yes, we can look at the remainder. Exactly. This is the procedure. So let us take a look at it. So what we need to do, if I have a number in decimal, it's difficult really to guess the number in binary. We need a method, okay, to convert the number in decimal to binary. And this method is simple. All what we have to do is we have to divide the number in decimal by 2. Now, why do we divide it by 2? Because the radix is 2. Okay, because we would like to convert it to binary. So binary means the radix is equal to 2. Let us take a look at this example. Now, when we divide a number by 2, you get a quotient and you get a remainder. This is integer division. Okay, so what we have to do is that we have to look at the remainder. Okay, so the remainder here can be either 0 or 1. Okay, when you divide a number by 2, you can only have two possible remainders, either 0 or 1. If the number is even, the remainder will be equal to 0. But if the number is odd, then the remainder will be equal to 1. Let us take a look at this example. Suppose I would like to convert 37. Now this 37 in decimal, I'm writing 10 here to emphasize that this 37 is decimal, okay? I would like to convert it to binary. So in order to convert the number 37 to binary, I'm going to divide 37 by 2. Now, when you divide 37 by 2, you get 18, okay? In fact, you get 18.5. But since we need to do integer division, so the integer part is 18, but you multiply 18 by 2, you get 36. You see 36, you can say 37 minus the 36, the remainder is equal to 1. So this is how we calculate the remainder. In fact, you can see that the remainder is equal to 1 because the number is odd. 37 is an odd number. It's not an even number. So this is the remainder. Now this will be the least significant bit. We take the 18 and divide it by 2, we get 9, and the remainder is 0. Take the 9, continue dividing it by 2, you get 4, and the remainder is 1, because actually 9 is odd. Take the 4 and divide it by 2, you get exactly 2, and the remainder is 0. Okay, take the 2, continue. So basically, we continue to divide the quotient by 2. You get 1, and the remainder is 0. Take the 1 and divide it by 2. Now, 1 is less than 2. Okay, so when you divide 1 by 2 and the dividend, so here we have the dividend is less than the divisor. Okay, so 1 is less than 2. You get 0 as a quotient, and the remainder is equal to 1. Okay, so you can see that the remainder is equal to 1, which is basically the one that appears here on top. Okay, so therefore this is the dividend, okay, which is equal to the 1, the divisor equal to 2. So basically when you divide 1 by 2, you get 0. So 0 multiplied by 2 is 0. And therefore when you subtract, you get the remainder is equal to 1. Now when we stop when the quotient is equal to 0. Khalas, we don't really continue. So now we can see that we can say that the least significant bit is equal to 1. The most significant bit here is this one, and we stop when the quotient is 0. So I can write now that 37 can be written in binary. Now we write it backwards. So this one appears here. Okay. If I would like to draw an arrow, okay, let me use here my pen tool. Okay, so you can say that this one here is this one here. And this is the most significant bit which appears here, okay? You can see that clearly. So basically the remainder, okay, are the bits of the binary number, and we write them backwards, starting from the least significant bit to the most significant bit, okay? So the number can be read as 100101, and this number is 37, okay, in decimal. In fact, you can convert it back from binary to decimal to check that your conversion was done properly. So if you add 1 plus 4, you can skip these zeros. So this will be 1, this is 4, this is 32. So 32 plus 5 is equal to 37. So therefore, the conversion was done properly. Is this clear? This is basically the conversion procedure. You can take any number in decimal and we can convert it to binary. Okay?
Doctor,
what
if the decimal number is 37.6 or 0.7? The answer would be the same, yes?
Well, if you have a fraction, then the fraction has to be converted separately. Here I'm talking about an integer, okay? It does not really have a fraction. So we are talking, I'll talk about fractions later, and I'll talk how we can represent fractions in binary. That's a different topic. I did not talk about fractions, so the focus is on integers. So I said here, okay, converting a decimal integer, right? It's an integer. Remember that, okay?
Okay.
If it's a fraction, it's a different procedure.
Okay.
I'll come back to it later. Right. So fractions will be my topic,
Doctor?
inshallah, on Thursday. I'll talk about fractions.
I think there is another way, but I'm not sure. So 32, if I wanted to convert it, I need 32 plus 4 plus 1, right? So
this will
I
be
can
guessing. This will be guessing.
Yeah.
Okay. Yes, of course you can do it this way. You can actually guess the weights and the bits. Okay. You can say that actually, okay, what is the near? So 37. You can say that 32 is close to 37. So you subtract. Okay. And you see when you subtract 37 minus 32, the remainder is 5. So you see that 4 is close to 5. So you subtract, and what is left is 1. So you can say that 37 is 32 plus 4 plus 1, but this will be guessing. Okay, this guessing will work if you are dealing with small integers, but if you are dealing with large integers, you need a procedure, a method that will discover the. Okay. Okay, so now let us move on. Okay, so if I would like to convert from decimal to binary, what I have to do is that I have to divide. So my number n here, okay, is in decimal. I can actually write it. I can expand it like this. So I can say this is digit 0, or bit 0 must be multiplied by 2 to the power 0. D1 is multiplied by 2 to the power 1. D2 is multiplied by D2 squared, and so on. Now, if you divide this n by 2, okay, you divide actually everything by 2. Now, D1 multiplied by 2 divided by 2, you get D1. D2 multiplied by D squared divided by 2, you get D2 multiplied by 2. And Dn minus 1 multiplied by 2 to the power n minus 1 divided by 2, you get 2 to the power n minus 2. Now, D0 is just multiplied by 1. So the remainder becomes D0. So when you divide n by 2, you get the quotient. This will be the first quotient. Quotient 1 is equal to this number here, and the remainder 1 is equal to D0. So we have discovered the first remainder, which is the least significant bit of the number. Now you take this quotient 1 and divide it again by 2, you get quotient 2. And you get the remainder 2, which is equal to D1. So this D1 becomes the second remainder. And you continue dividing by 2 until you have discovered D2, D3, all the way to Dn minus 1. So you discover all the bits of the number. So this is actually a mathematical proof that the method works. Okay, so this is why we divide by 2. And this is how we obtain the bits of the binary number. Okay, so D0, D1, D2, D3, and so on. These are the remainders. So the first remainder is D0, the second remainder is D1, and so on. And these are the digits or the bits of the binary number. So this is why we continue and repeat dividing the quotient by 2 until the quotient becomes 0. So we stop when the quotient becomes equal to 0. Okay, and the remainders will become the bits, okay, of the binary number. And we have the first remainder will be the least significant digit, and the last remainder will become the most significant digit of the binary number. Okay, so this is basically an explanation why the division by 2 is the method to obtain the bits of the binary number. Now, there are some popular number systems that people use. We have seen that for computers, we have to use the binary number system, and the radix is equal to 2. However, we as human beings, we use the decimal number system, and decimal means that the radix is equal to 10. That actually is the decimal number system. So computers, okay, need to use the binary, which is radix equal to 2, because it's easier to design the circuits, okay, using the binary number system, whereas us as a human beings, we are used to the decimal number system because our ancestors, okay, have discovered, okay, the decimal number system by using their fingers, okay, by counting using their fingers. This is why decimal is natural to us, whereas binary is more convenient to computers. Now we can actually use other number systems. Mathematically, you can use any number system. For example, the octal number system, the radix is equal to 8. So 8 means octal, okay? So octal here means that we have 8 digits, and these are from 0 to 7. We always start at 0, and we stop here at the radix minus 1. So the radix is 8, so therefore we stop at 7. In 10, we start from 0, and we stop at 9, okay? Now notice that 10 consists of 2 digits, 1 and 0. So therefore, if you want to write the number 10, you have to write it as 1, 0 in decimal. In the case of 16, we call it the hexadecimal number system. So hexadecimal, it means that the radix is 16. So in the case of 16, we have to use the first 10 digits, okay, in decimal from 0 to 9. So these are from 0 to 9. But we need 6 more digits. But there are no more decimal digits because there are only 10 decimal digits. So therefore, we use letters as digits. So now we use letter A becomes 10, B becomes 11, C becomes 12, okay, D becomes 13, E becomes 14, and F becomes 15. So therefore, we use 6 letters from the alphabet as, as digits in the hexadecimal number system. So therefore, we have to refer it to a single digit. Okay, we cannot write it as 1, 0. So we have to write A, and A will be the digit 10, and B will be the digit 11, and F will be 15. So you have to remember these in the case of hexadecimal because we are using 16 digits. So we need 6 extra digits, and we use them as letters. Now, there is an easy way to convert between octal and hexadecimal number systems and binary because they are related. So people, programmers, okay, when they are programming, rather than using binary, it's actually easier for them. It's actually more convenient to them to use octal and hexadecimal. Now, octal is 8, and 8 is 2 to the power 3. Hexadecimal is 16, and 16 is 2 to the power 4. So there is an easy way to convert between binary, octal, and hexadecimal. Let us take a look at this. Now, this table here shows, okay, the binary, octal, hexadecimal, as well as decimal. These are the most popular number systems. Okay, so I'm showing here, okay, the decimal values, okay, starting from 0 all the way to 9. This will be a single digit, okay, in decimal. And then I'm going to 10, 11, up to 15. Now, the reason why I'm going to 15, because I can represent it with a single digit in hexadecimal. So in hexadecimal, 0 to 9 are exactly the same way, 0 to 9 in decimal. So here we have it 0 to 9, and here I have it 0 to 9 in hexadecimal. They are identical to the digits in decimal. But 10 is written as 2 digits in decimal. We can write it as a single digit in hexadecimal. So 10 will be A, 11 will be B, and we can go all the way here to 15. 15 will be F. Okay, is this clear? These are the 16 digits in hexadecimal. In the case of binary, we need actually 4 bits to represent the decimal values from 0 to 15. So 0 will be in binary. If I use 4 bits in binary, 0 will be 0, 0, 0, 0. Okay, 1 will be 0, 0, 0, 1. 2 will be 1, 0. Okay, 0, 0, 1, 0. So that's 2. 3 will be 0, 0, 1, 1. 4 will be 0, 1, 0, 0. This one will be 4. This is 5, and so on. And finally, 15 will be 1, 1, 1, 1. Notice that this is 8 plus 4 plus 2 plus 1. This will give you 15. Notice that 10 is 1, 0, 1, 0 in binary. This is 8 plus 2, will give you 10. Here 9 will be 1001. That's 9. It's 8 plus 1. 8 is 1000. This one is the 8. Okay? Is this clear? Now, this table is so important when you would like to do the conversions between binary, octal, hexadecimal. You can do it very quickly using this table. Okay? Now, notice that in octal, we only have 8 digits from 0 to 7. Okay? So these are exactly the same 8 digits that exist in decimal. So we go from 0 to 7. But there is no digit which is 8. So 8 will be 10 in octal. So 10, this is not 10. This is 10 in octal. So 10 is 8 because this one is multiplied by 8. 9 will be 11. It's 8 plus 1. So the most significant digit here is 1, which this most significant digit is the 8, and the least significant digit is the 1. So 8 plus 1 is equal to 9. And finally, here we have 17. It's actually 8 plus 7. So this 17 is not 17. It is just 17 in octal, which is 8 plus 7, which is equal to 15. Okay? Is this clear? So it's very important to remember this table because we can easily do the conversions between octal, hexadecimal, binary. We can do this kind of conversion very quickly. Right. Let me show you an example how we can do the conversions between these number systems. So remember that Radix 16 is 2 to the power 4, okay? And Radix 8 is 2 to the power 3. So this is why we chose 16 and 8, because they are related. They are power of 2. Now, because they are power of 2, as we have seen in the previous table, in the previous slide, okay, we can represent every hexadecimal digit with 4 bits. And we can represent every octal digit with 3 bits. Why? Because octal, we only have radix 8, 2 to the power 3, so we can use 3 bits to represent a single octal digit. Suppose I would like to take a number, okay? So given this number, which is shown in binary, okay? So this is a 32-bit number in binary. You can actually count the bits. If I would like to convert this number to octal, how do I do this?
We can divide the number into 3 bits. For example, we take first 3 bits from the right and convert them to the equivalent.
Exactly. So yes, this is what you are saying is correct. We have to group the bits, but we start from the right, from the least significant bit. So I'm going to look at this 100, right? So this is a group of 3 bits. So what is 100? What is 100 in octal?
4.
What is 100? It is 4, yes. In decimal, it's also 4, and octals will be 4. So therefore, we say that we take a group of 3 bits, starting from the least significant bit. So we start from the right. It's very important to start from the right, not from the left, because if you do it from the left, it will be totally wrong. So you have to start from the right. So 100 will be 4. Next, we have 010. It will be what?
1.
010 is what?
2.
2. Yes. 110.
12. 6.
110. 6.
5.
Yes.
5.
011.
5.
011.
3.
3. No mistakes, please. No mistakes. 010.
4.
010.
2.
5.
Yes, 2. 101.
5.
Yes, 5.
5.
101 again.
Another 5.
Okay. 000.
0.
0.
Okay.
0.
011.
3.
01.
5.
Okay. Finally, we have 11. Now these are only 2 bits, but we can always insert a 0 from the left. It becomes 011. Is what?
3.
Good.
3.
Good.
3.
I'm getting a echo for my voice. Type. Suppose I would like to convert it to hexadecimal. Okay, to hexadecimal. How do I do this?
4 bits.
We take 4 bits.
4 bits. So now I have to add, so it will become 0100. What is 0100?
Still 4.
Yes.
4.
Again 4, yes. 4 in hexadecimal. Then I have 1001. I have to take 4 bits.
9.
9. Yes. You see, this is why it's very important to remember the table that we have seen in the previous slide, so that we can do the conversion very quickly. Okay. So 0111 is what?
7.
Yes. Next, 1010.
11.
1010.
10.
10. What is 10? What is 10 in hexadecimal?
8.
It has to be represented by a single digit. How about 0110?
11. B.
0110.
6.
Oh yes, it's 6.
6, right. 0001. Please,
One.
let's go.
1.
Okay, next we have 1011.
This is 11.
11.
11.
What is 11?
B.
B.
B. And finally, we have 1110.
E.
Yes, it's 14. It is E. Exactly. Good. So now you understand how we can do these conversions quickly between octal, hexadecimal, and decimal. Okay. Right. If I would like to convert octal to decimal, this is very easy. All what we have to do is that we have to use the formula which is shown on top. So I have this number which is 7204 in octal. I would like to convert it to decimal, no problem. This is actually 4 multiplied by 1. This is just a 0. This 2 is multiplied by 8 squared, and this 7 is multiplied by 8 cubed. You use a calculator, you do the math, you get 3,716. Now, this is not 7,204. This is just 7204. This is how I read it. 7204 in octal is 3,716 in decimal. Let us take a look at this number. Now, this number is in hexadecimal. So you can also have digits like A, B, up to F. Now, this 3 is multiplied by 16 cubed because it has this position here. This B is 11, and it's multiplied by 16 squared. This A here is the 10. It's multiplied by 16, only 16 to the power 1, and this is just a 4. If you add them up, you get 15,268. Okay, is this clear? That's how we do the conversion to decimal. You can just take a number in any radix, just use the equation and evaluate, and you get the number. However, if I would like to convert the decimal to hexadecimal, I'm running out of time. What you have to do is, how do I convert decimal to hexadecimal? We can divide by 16. We can divide by 16. Anyways, I'm running out of time. Let me just pause here. Next time, inshallah, I will talk about this. I will finish this topic. I'll talk about fractions. Do you have any questions, students? Do you have time? So there are some important properties that we need to know about number systems. So the first question is, how many possible digits can we have in radix R? How many possible digits can we have in radix R? Pick any radix R and get, what is the number of possible digits? Anyone?
R.
R, exactly, R digits. What are these?
0 to R minus 1.
From 0 to R minus 1, yes, R digits. So for example, if we are dealing in binary, we have 2 digits from 0 to 1. If we are dealing in decimal, it will be 10 digits from 0 to 9. Excellent. So what is the result of adding 1 to the largest digit in radix R? What is the result of adding 1 to the largest digit in radix R?
Return back to the smallest digit.
Yeah, for example, if you are in binary, let us take decimal. Decimal is easier. So what is the largest digit in decimal?
9.
Okay, if you add 1.
You are 0, 0, 1.
It will be 10. 10 is written as 1, 0, right?
Yeah.
So it will be 1, 0 in radix R. if you are in binary, the largest digit is 1. If you add 1 plus 1, what do you get?
0 and 1 carry.
Yeah, so you got 1 0. So 2 will be 1 0 in binary, exactly. So 0 and the carry. So we write it as 1 0. Right. So therefore, since our digits, so we don't have the digit R in Radix R. So if you add 1 plus the largest digit, you get 1 0 in Radix R. Okay. Here are some examples. 1 plus 1 in binary will be 1 0. So 1 0 in binary will be 2. If you add 7 plus 1 in octal, you get 8, but 8 is 1 0. Okay. If you add 9 plus 1 in decimal, you get 10, but 10 is also written as 1 0. If you do it in hexadecimal, if you add F is 15, you add to it plus 1, you get 16, and 16 is written as 1 0 in hexadecimal. So you see that we are getting 1 0, but 1 0 has different meanings. In binary, 1 0 is 2. In octal, it is 8. In decimal, 1 0 is 10. And in hexadecimal, 1 0 is 16. Is this clear? So we write it 1 0, but it has actually a different value in different number systems. Clear? Is this clear?
Yes, it's clear.
Yes, clear.
Okay, very good. So now let me just ask you this question. What is the largest value using 3 digits in Radix R? Yani, for example, if we are using decimal, what's the largest number that you can represent it with 3 digits?
It is the summation of
999.
Exactly, 999, 999. Yes. Okay, if it is in binary?
111.
If it is in octal?
777.
If it is in hexadecimal?
15.
F. We write F. Okay, exactly. Now, 999 is equal to what? 999, we can write it as 10 to the power 3 minus 1. Okay, it's 1000 minus 1. You agree?
Yes.
Type 111 in binary, it's equal to the value of what?
2 to the power 3 minus 1.
It is 7. 7 is actually 8 minus 1. 2 to the power 3 minus 1. And if you look at octal, 777 will be 2 to the power, it will be 8 to the power 3 minus 1, and so on. So if you look here, for example, in binary, 111 is written as 2 to the power 3 minus 1. 777 in octal, it's 8 to the power 3 minus 1. And in decimal, 999 is 10 to the power 3 minus 1. So you can see it's the radix here. The radix raised to the power 3, because we are using only 3 digits, minus 1. So for any radix R, you can see that the largest value using 3 digits will be R to the power 3 minus 1. Okay? Is this clear?
Yes, clear. That's one.
Okay. Let us move on. Okay, how many possible values can be represented using n binary digits? If I use n binary digits, how many possible values you can have?
2 to the power
to the n.
Yes.
Minus
so it's
1.
actually 2 multiplied by 2 multiplied by 2, because each digit in binary can have 2 values, right? So it's 2 multiplied by 2 multiplied by 2 n times. It's 2 to the power n. So we have 2 to the power n values. The smallest will be 0, and the largest will be 2 to the power n minus 1. Because we started at 0, then the largest will be 2 to the power n minus 1. But if you use n octal digits, how many possible values you can have if you use n octal digits?
8 to
n minus 1.
8 to the power
n minus 1.
So you start from 0, you end at 8 to the power n minus 1. Yes. And how about if you use n decimal digits?
10 to the n minus 1.
It will be 10 to the power n values. You start at 0 and you end at 10 to the power n minus 1. Exactly. How about n hexadecimal digits?
16 to the n minus.
Yeah, so the total values will be 16 to the power n. The smallest will be 0. The largest will be 16 to the power n minus 1. Of course, we are not really counting here. We are not really dealing with negative numbers. We are dealing only with unsigned integers. I'll talk later about negative numbers because this will change. You can use binary numbers to represent also negative values. But I'll talk about these later. Okay, I'll come back to them later. So here we are dealing with unsigned integers. Okay, make it like this. طيب. Now, let us. Can you see me, or okay? I need to turn on my camera. Can you see me now?
Yes.
Yes.
Yes. Okay.
Yes.
Good. Right. So that's actually, these are important properties of number systems. If you'd like to use n digits in radix R, okay, how many possible values can be represented?
R values.
R to the power.
R to the power n.
Exactly, R to the power n. The smallest will be 0, the largest will be R to the power n minus 1. So this is the rule, okay?